The topic of our case study is the validation of a high-performance liquid chromatography method to quantify Thymol in nanocapsule of bioactive essential oil from nuclear acidosis. And this is our group member, which is Rafat bin Atira binti Muhammad Azmi, Syazwana binti Sadat, and Nur Amelia Shazlin binti Muhammad Isal. Hi, my name is Syazwana binti Sadat. I would like to present the introduction based on the journal that I have studied. Northeastern Brazil is home to the aromatic scalp Piacidoides camberbernaceae, also known as rosemary pepper. Its leaves are used to make essential oil, and these oils are highly concentrated in thymol, which has strong antibacterial properties. According to studies, the essential oil from L-Cidoides possesses numerous biological qualities, including topical, anti-inflammatory, antibacterial, and antifungal effects. However, other studies claim that when the essential since one of the goals of nano-encapsulation is to reduce toxic effect while maintaining or improving treatment effectiveness, the essential oil of L-Cidoides was therefore enclosed in polymeric nanocapsules. One of the quantification methods frequently employed in the pharmaceutical industry for drug analysis is high-performance liquid chromatography, which has been a popular approach for examining pharmaceuticals delivered in nanocarriers. Gas chromatography analysis methods are often used for essential oil, but the primary constituent and pharmacological marker in L-Cidoides essential oil, thymol, has an absorption spectrum in the ultraviolet area. Due to this characteristic, thymol can be quantified in essential oil, plant extract, and nanocarriers using HPLC-UV and HPLC-DAD, as has been mentioned in numerous research. Therefore, the objective of this investigation was to validate an analytical methodology for quantifying thymol in L-Cidoides essential oil and nanocapsules containing that oil using HPLC-DAD.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Amelia Shazlin binti Muhammad Isal, and for today's video, I'm going to talk about the materials and methodologies of the article that I have read. There are the total 9 of reagents, solvents, and material. The first one is thymol, PLGA, Polosummer 188, acetone nitrate grade HPLC, acetone grade PA, water purified through millicurie filter system, phosphatidylcholine, essential oil of lepracidotes and millets LCR filter with PTFE membrane module 0.45 micrometer. The next one is instrumentation. There are 3 instrumentation that were used. The first one is liquid chromatography with diode array detector. The next one is rotary evaporator, and the last one is magnetic steering. Okay, next we will move to the methodologies. There were 4 methodologies that were used. The first one is the preparation of nanocapsule. By nanoprecipitating a premixed polymer, a blank nanocapsule NCB and a nanocapsule containing L-Cidoides essential oil were produced. At 40 degrees Celsius, PLGA 36 mg, phosphatidylcholine 90 mg and 0.1 gram were dissolved in 15 ml of acetone. Under magnetic stirring, this organic phase was injected into an aqueous phase containing Polosummer 188 100 mg and ultra pure water 30 ml at 40 degrees Celsius. Acetone was removed after 10 minutes and the suspension was decreased to 10 ml at reduced pressure rotary evaporator. The identical procedure was used to make a blend nanocapsule, but the organic phase did not contain any OELS. The next one is the chromatographic parameter. The chromatographic condition was shown in the slide, which is the column temperature is 40 degrees Celsius. The mobile phase is acetone nitrate ratio with water at 78 ratio to 22. It is in the isocratic elution and the flow is 0.8 ml per minute, and the detection wavelength is 278 nanometer, and the sample injected volume was 20 microliter and the runtime is 8 minutes. The mobile phase was sonicated for 30 minutes to degas it and then vacuum filtered through a 0.45 meter filter before being introduced into the system. This experimental setting was created based on the technique that had previously developed for measuring the amount of thymol in L-Cidoides leaf extract. The mobile phase was added into 10 ml of volumetric flask after 10 mg of the thymol reference standard was placed in there. To create a calibration curve, the thymol stock solution were made from using the 8 dilution. These are the 8 dilution that were used to make a thymol stock solution. The next one is the preparation of sample solution. Using the analytical balance, 20 mg of OELS were weighed directly into a 10 ml of volumetric flask, and the volume was then filled with the mobile phase to create an OELS sample. solution between 16 and 24 mg/ml -1 OELS were made from this solution, which is 2 mg/ml -1 OELS as needed for the test. In order to prepare a sample of NCLS or NCB, 80 until 100 liters of the sample were added to 10 ml volumetric flask, and then the remaining volume was filled with the mobile phase. On the day of the analysis, the standard and the sample were always made, filtered through a 0.45 m membrane, and then transferred to a vial for injection. There were 6 method validation, which is the first one is specificity. Comparative analysis of the Thymol OELS and CLS were performed to assess specificity. The next one is linear rate, which is the detector respond to different concentration of Thymol OELS and CLS. The next one is the intermediate precision, which is 3 concentration of OELS and 3 concentration of NCLS, corresponding to 80, 100 and 120% of theoretical concentration. The next one is the repeatability, which is performing 6 determination of OELS and 6 determination of NCLS at concentration of 20 and 10 microgram ml -1. Precision is investigate with respect to repeatability, intraday precision and interday precision. Intraday precision is repeatability and interday precision is intermediate precision. The last one is the limit of detection and quantification, which is standard deviation of the data and the intercept average slope obtained from calibration curve of Thymol standard.
My name is Atira binti Azmi, and I will be presenting about results and discussion. So here's our 4 diagrams, which is A, B, C, and D. A diagram representing a peak of Thymol and spectrum. B, peak of Thymol ELS viewed by HPLC AD observed at 9 minutes. C is blank nanocapsules, and D are peak of Thymol capsule. The chromatography graph analysis showed that the NCB excipients that make up the metric of the nanocapsules Thymol did not interfere with the analysis by this method, since there was appearance of other peaks in the gram. It was noted that the selectivity method was specific quantification of NCLS. The analysis of the linearity parameter gives the information about the method to provide results which are proportional to the concentration of the analyte that contain. Here's figure 2, which is graph of calibration curve obtained by HPLC DAD, representing all of the 9 concentration of Thymol from 4 to 180 microgram ml -1. So in figure 2, the analysis of the linearity parameter gives the information about the method to provide results which are proportional to the concentration of the analyte that contained in the sample. Analysis of the variance was used to find the linearity of LS and NCLS within the Thymol concentration range 4 to 180 microgram per ml. They used to calculate the linear regression using the method of least squares. The correlation coefficient R for the analytical curves interpolate with 7 standard concentrations of Thymol 0.9994, and the equation of the straight line that was produced was in the form of y equals to ax plus b, where y is the area and x is the concentration of the substance, while y is the linear function of x. Thymol's analytical curve is depicted visually in figure 2, along with its related equation y equals to 592x minus 199e. The NCLS and the oil concentration curves for the 5 analyzed concentration display correlation coefficient of R 0.9991 and 0.9979 respectively. The examination of the waste graph is a crucial component in assessing the linearity of the approach. To this study, curve fitting issues such as linearity deviation, the presence of atypical simple heteroscedasticity, and error dependency can be identified. As a result, the adjust curve means error with uniform distribution, a zero mean, constant variance, and no exceptional strains. So here is figure 3, which is graph representation is related to 5 concentration of CLS and A and NCLS, which is B. So figure 2 illustrates the waste curve, the area between CLS and NCLS that found to be normally distributed and independently distributed about 0, that there is no waste between these 2 points. This can be thought as an estimate of the model error because it represents the amount of data variability that is not explained by the adjustment. Thus, the graphical portrayal of waste must be normally distributed independently around 0 and have a mean of 0, also have a variance that is constant. This tendency was evidence that the disgraphic pattern of Thymol, OELS, and NCLS in the current investigation. The analysis of variance ANOVA for the Thymol, OELS, and NCLS calibration curve showed that no significant linear deviation, B equals to 0.57, 0.39, and 0.20 respectively. We can conclude that they represent a phase response linearly to a Thymol detector in the range of 480 microgram per ml. The limit detection LOT and limit of quantitation LOT might be calculated using a trustworthy calibration curve range thanks to the statistically analysis of data related to the linearity of the quantification limit for the Thymol test was 1.02 microgram ml91 while the limit of detection 0.5 microgram ml91. Here is table 2. Table 2 is representing Thymol quantification results in OELS in a single day regarding the repeatability test within a condition. And table 3 is Thymol quantification results in NCLS performed in a single day regarding the repeatability test within a condition. So table 2 and table 3, the concordance of results at repeatability level in one condition and intermediate precision examined with accuracy test in the run condition RST value 1.05 and 2.22 respectively, shown by the OELS and NCLS repeatability at 100% of the theoretically test concentration. Results are present for the table. The results are present as the minimum content of Thymol in OELS with 100% content goes to 600 mg of Thymol per 1 ml of OELS based on mean and standard deviation of 3 replicates. While table results are expressed as a normal content in NCLS based on the mean and standard deviation of the 3 replicates with 100% of theory is equivalent to 3.0 mg Thymol per 1 ml NCLS on average. Table 4 represents showing the quantification of Thymol LS, while table 5 showing quantification of NCLS. So, in table 4 results are written as the shown content of Thymol LS with 100% content of equals to 600 mg of Thymol per 1 ml of LS based on the standard deviation of 3 replicates. The test result for intermediate position to run positions. While table 5 results are represented as a nominal Thymol content in NCLS based on the mean and standard deviation of 3 replicates, where 100% of theory is equivalent to 3.2 mg of Thymol per 1 ml of NCLS on average. So table 4 and 5 is representing the RST values of ELS and NCLS respectively varies from 0.9 to 3.09 and 0.4 to 3.79 in the evaluation of the intermediate position table. Table 6 is showing static evaluation of results for the intermediate position test for ELS. And table 7 is a static evaluation of results for the intermediate position test for NCLS. Table 6 and 7 as shown LS and NCLS, the F-test of ANOVA to assess the homogeneity of variance in the intermediate accuracy test with significant variation between the analyses performed by different analytes or on a variance day P greater than 0.05. We may therefore conclude that the procedure is accurate based on findings. Here is table 8, which the results of the recovery method from essay in ALS, and table 9 is the table that includes of jerk, provider, and participant of the measure method of Thymol. So, the 8 and 9, the accuracy test demonstrate the effectiveness of the technique for estimating the amount of analytes in the sample. According to the degree of systematic mistake to the process is used to express the accuracy. Though in analyte recovery, the extraction procedure, erroneous volumetric measurements, or interfering compounds in the sample all contribute to systematic mistake. Table 8 presents the accuracy of the analysis finding for the OELS and NCLS at 3 concentration levels. As can be shown, the quantification of Thymol ELS, the method has a recovery for about 97% with an RST of 1.04 and for NCLS a recovery of 9.82% with an RST of 1.97. By adjusting the temperature parameter for the the mobile phase look and the column manufacture of the robustness of the approach was evaluated. Table 9 shows that none of the characteristics had a statistically significant effect on the dose of active time f of active, with p equals to 0.3929. The robustness thus detect that the component of the method that significantly increases the finding, and foresee issues that might occur when the method is applied to various instruments, reagents, chromatographic columns, and the environments. As a result, we can conclude that the result that the quick approach is reliable to the parameter that we put to the test. That was all. Thank you.
For the conclusion, according to the journal, the study's findings show that the approach can be used to quantify thymol using HPLC-TAD for sensitive measurement of the active thymol in essential oil as well as the nanocapsules containing the essential oil of L-sidoices. The approach was shown to be straightforward, quick, specific, linear, accurate, and robust. The analytical process has an 8-minute total analysis time, allowing for the analysis of several samples quickly. As a result, it is appropriate for routine analysis of both the OELS raw material and the creation of OELS containing nanocapsule. The method simplicity makes it suitable for use in lab without access to advanced analytical equipment like LCMS or GCMS, which need a more involved, expensive, and time-consuming analysis.